Good evening to you all. I am hoping that you're doing well during this pandemic. I am Brian Immanuel B. Rabe, a graduate student taking up the degree of Master of Science in Civil Engineering. Today, I will be discussing my master's thesis, a multi-criteria decision analysis of building energy retrofit through a whole building simulation, under the guidance of Dr. Jason Maximino C. Ongpeng. Now, it is fair to wonder why I've chosen this particular topic. 3 years ago, my only motivation of pursuing graduate studies was self-improvement and boosting my career as an engineer. But over these years, after taking up several courses, issues of sustainability became a topic of my interest. Problems were identified, and as a civil engineer, it is my duty to be part of the solution. The presentation will be divided into 5 parts. First, the introduction, followed by a pertinent review of literature, the proposed methodology of this work, followed by a brief description of the case study and the presentation of data. Finally, conclusion and recommendations. To give you a preview in this work, a multi-criteria evaluation of energy retrofit strategies using 3 performance criteria was achieved. The study will also highlight the feasibility of a net zero energy building through a whole building energy simulation software design builder. And lastly, a compromise retrofit scenario was proposed in accordance with performance metrics and stakeholders' preference. To start, an aggressive construction industry complements economic growth. Construction developments such as buildings, bridges, roads, and networks can be a benchmark for a country's economic boom. However, this same industry is also one of the most energy-intensive, resource-depleting, and pollution-emitting sector in the world. As humans, quality buildings are needed to safely house our schools, hospitals, offices, and homes. However, constructing and operating new buildings are challenging due to limited resources. For this reason, extreme efforts are undertaken by countries around the world in highlighting energy efficiency and low carbon growth into their long-term plans and targets. It is a fact that old buildings are poor energy performers. These buildings are often found in a state of abandonment and face limited options as they approach its end of life. These options are typically demolition, abandonment, and adaptive reuse. According to Webb, retrofitting is a complex task in which many criteria are balanced to achieve the long-term goal of a building. Moreover, the decision of whether to retrofit or demolish an aged building is not always straightforward. It is challenging since it involves substantial funding and decision-making from a wide range of stakeholders with constraints, limitations, and assumptions. According to CAT, decision-making in assessing outcomes of complex situations involving many intangibles is difficult. In response to this problem, this work proposes energy retrofit strategies, or ERS, to make buildings more sustainable. ERS should consider a balance between the triple bottom line of environment, economy, and social. However, it is impossible to achieve this balance due to the trade-offs of conflicting and incommensurable criteria. Thus, in this work, a multi-criteria decision analysis, or MCDA, retrofit framework to achieve a net zero energy building in the Philippines was proposed. While in line with this, while in line with this, the study aims to achieve the following specific goals. First, to assess ERS in terms of their environmental, economic, and technical performance trade-offs. Next, to determine the impact of ERS on a case study building. Third, to establish the feasibility of a net zero energy building through building energy simulation. And lastly, to propose a compromise solution between retrofit scenarios based on stakeholders' preference and performance criteria. Incorporating energy efficiency measures into the design, construction, and operation of new and old buildings can significantly reduce energy use. For instance, the concept of net zero energy building is developing and promoted around the world. Currently, there are various definitions that describes NZE, depending on the boundary conditions and the metric to be followed, as described in Table 1. Buildings which produce as much energy as it uses over the course of the year are net zero site energy buildings. Examples of these are the Indira Paryavaran Bhawan in India, the Pearl River Tower in China, and the National University of Singapore SDE4. While in the country, the Artalan Century Pacific Tower can be classified as a net zero emission building. It is the only triple certified project in the Philippines, having received, in addition to the EDGE Zero Carbon certification, the LEED Platinum rating, and the Verde 5-star certification, the highest and most prestigious categories in green building rating standards. In this work, net zero energy will be limited to the site energy. Sustainability is a word we hear more often today. In the year 1987, the Brundtland Report gave this definition of sustainable development. Although vague, this became the foundation of the sustainability concept. Today, sustainable development goals were set as a blueprint to achieve a better and more sustainable future for all. Promoting energy efficiency to both new and existing buildings is a priority in most countries today. However, in the local setting, the Philippines is lagging compared to other countries in terms of energy efficiency frameworks and regulations. In order to achieve the goals aforementioned, studies today are more inclined towards the use of eco-efficient materials and energy-saving measures. One method to prolong the service life of old buildings is retrofitting. Retrofitting is the act of providing something with a component or feature not fitted during manufacture or adding something that it did not have when the first constructed. It should involve applying an integrated whole building process. However, in energy retrofits, it may be applied only to key elements in the building such as walls, roof, glazing, electrical and mechanical system. While several studies focus on a particular element of a building, some explored ERS on the building as a whole, with various parameters such as type, climate, occupancy, and use. As previously discussed, the concept of net zero energy building is developing around the world. Theoretically, studies have explored the feasibility of a net zero energy building using various energy retrofit strategies, multivariate criteria, and validation methods. It should be noted that most of these studies prove that NZEB is feasible given appropriate analysis and methods. This figure presents the conceptual framework of the study. In this work, a case study was modeled in Design Builder, using various building data and information. Next, ERS were then integrated individually on a case study building, then cumulatively through retrofit scenarios. These retrofit scenarios were based on calculated performance criteria of environment, economic, and technical metrics. Two MCDA methods were used to determine the compromise solution: analytical hierarchy process or AHP, and Vicar as the weighting and ranking method respectively. To test the robustness of the model and the methods used, a sensitivity analysis was done on the MCDA tools used. The methodology of the study was divided into three folds. First, a discussion of the building simulation process. Next, energy retrofit strategies considered in the study, and post-retrofit scenarios will be presented as well as the input, output, and methods for performance criteria, and lastly, the proposed AHP Vicar method as the multi-criteria decision analysis tools. The preliminary modeling was the initial stage of the study, where all pertinent information and necessary data gathering was done. This step entailed collecting and identifying the general information about a target building. This includes gathering details such as floor plans, construction details, occupancy, schedule, weather data, and many more. For other relevant data that were not available, related literature and online sources were used instead. Next, a calibrated simulation is an appropriate method to measure and assess the accuracy of the baseline scenario and determine the impact of post-retrofit scenarios. In a study by PAN, an allowable tolerance of 15% and 10% for monthly and annual coefficient of variation should be met respectively. For this study, simulation results were limited to the analytical model calibrated using the monthly utility bill. Once statistical indices are met, it is safe to say the calibrated model behaves like the target building. The figure in the left presents the building as modeled in Design Builder, while figure 4 illustrates run 1 of the simulation and calibration process. The goal of the study was to examine the impact of ERS when applied to a case study building. The results are intended to be presented to stakeholders to promote the use of ERS to reduce the energy consumption of a building and at the same time have a balance between eco-efficiency, cost optimality, and technical performance in the process. For this study, 6 elements of the building comprising of 18 ERS as shown in this figure were evaluated individually and cumulatively grouped through retrofit scenarios. Other ERS and retrofit scenarios unstated will not be part of the study. Each strategy was evaluated using 3 performance metrics, environmental, economic, and technical with the use of six sub-criterions. The environmental criteria include two steps. First, identifying the inventory components and developing the life cycle impact assessment models to transform the environmental burdens to impact categories. In this study, three damage categories was considered: damage to human health, damage to ecosystem quality, and depletion of natural resources using CIMA Pro. Next, a detailed unit price analysis was done to determine the investment cost and return on investment as sub-criteria for the economic metric. Lastly, the energy potential was extracted from Design Builder. This process was repeated for each retrofit strategy. The performance metric derived from the previous method was used in the MCDA phase. The first step entails identifying the weights of each performance criterion. Stakeholders from various disciplines were invited to form individual pairwise comparison using a pairwise comparison scale. It was assumed that the instruments in the study provided reliable data and the respondents fully understood the questions they were asked and provided an honest expression based on their knowledge. These weights and performance metrics were then calculated using the Vicor method. A sensitivity analysis was done to determine how alternative weighting methods affect the compromise ranking and how rankings change using alternative ranking methods. To summarize the methodology, the objective of the study is to propose a MCDA retrofit framework to assess the feasibility of a net zero energy building in the Philippines. Relevant information to the building were modeled, simulated, and calibrated using Design Builder. ERS were then subjected to a LCA to determine the three damage categories using CIMA Pro and Eco Indicator 99, as well as economic evaluation that determined the initial investment cost and return on investment. Next, ERS were simulated individually and cumulatively and were grouped into six retrofit scenarios that determined the technical performance of a case study building. MCDA was done in three folds: AHP that determined the criteria weights, Vicor as the ranking method, and a sensitivity analysis that tested the robustness of the model. The case study building chosen for the study was the National Engineering Center, located in UP Diliman. This building serves as the UP College of Engineering's research and extension arm. The four-story building with basement is characterized by its brutalist architectural features and having an open area in the center of the building. The building primarily contains classrooms, laboratories, and offices on the first and fourth floors. Other relevant characteristics of the building is described in the table shown. The three-year actual energy consumption from 2016 to 2018 of the National Engineering Center building were compared to the data extracted from the calibrated model using Design Builder. In the figure above, the calibrated model was the result of multiple simulations and iterations. It can be observed that all months are within acceptable tolerances. In general, the annual energy consumption of the calibrated model has a variance of 5,000 kilowatt per hour, or 1% lower than actual energy consumption. This demonstrates that the model is ready to move forward with the application of proposed ERS. A cradle-to-gate life cycle assessment was done to 18 retrofit strategies considered in the study. This figure presents the environmental damage of each ERS in terms of endpoint damages. In general, the figure shows higher damages on human health rather than on damages to ecosystem quality and depletion of natural resources. This can be attributed to the volume of raw materials used on the production. Moreover, it can also be derived that on-site generation strategies R16 to R18 significantly contribute the largest among the group. Prioritizing the most economically promising investment is not always straightforward. Several real-world constraints must be considered. In any type of investment, the cost of capital is critical to make better decisions on how to allocate resources. This figure presents the initial investment cost and the energy potential for the energy retrofit strategies. As previously mentioned, on-site generation strategies contribute a considerable impact in terms of environmental damages. Similarly, these types of strategies require a hefty amount in investment costs, but it should be noted that these contribute to almost 40 to 50% of the energy requirements of the building. On the other hand, strategies targeting the building envelope R1 to R9 perform poorly in terms of energy potential. No significant reductions in energy consumption were achieved regardless of the type of strategies used. To further illustrate the impact of strategies, this figure shows the normalized economic and technical impact of each ERS in comparison with the other. In prioritizing an ERS, it is ideal to select strategies that fall in quadrant 2. It provides significant energy potential and the least investment cost. However, none of the ERS fall in this quadrant. In terms of energy potential, ERS in the first quadrant should be considered despite its economic trade-off. Alternatively, strategies that fall in quadrant 3 and 4 are low-impact strategies that should be given the least priority. Finally, this figure illustrates the normalized performance evaluation of each ERS. Evidently, there is a trade-off between each performance criterion. For instance, the energy potential of on-site generation strategies is noticeably quite significant despite its high investment cost. Alternatively, those strategies with lesser investment costs perform poorly. To sum up, the results of this work prove that the environmental, economic, and technical performance of ERS are inversely proportional. Furthermore, the impact of ERS was determined and it was identified that the performance trade-off was clearly present. It should be noted that combining the best strategy from each category could result in compelling energy savings to achieve the long-term goal of a building. Based on the previous results, ERS were grouped into retrofit scenarios. It should be noted that numerous combinations are possible. However, the approach considered in this work is described as follows. Strategies that were most impactful in reducing the energy consumption per category were selected for the net zero energy scenario. It should be noted that the best strategy for each group was selected solely based on its technical performance, while ERS with least environmental impact was selected for the eco-friendly scenario. 3 retrofit scenarios that focus on a particular building element sum up the retrofit scenarios considered in the study. This study challenged the feasibility of a net zero energy building by incorporating ERS. As previously mentioned, the National Engineering Center building was chosen as the case study. In order to achieve the net zero energy goal, it is quite logical to identify the maximum on-site potential in order to give a minimum target to be met. The on-site generation strategy generated 49% of the energy requirements of the building. Having calculated the maximum site potential, the energy reduction required to achieve the net zero energy target of the building is shown in Figure 11. ERS, the target the building envelope, was simulated for the first 3 runs. It was found out that there were diminishing returns as ERS were simulated cumulatively as illustrated in run 3. Instead of a 20.56 energy reduction, only 10.42 was attained. On the other hand, significant energy savings were attained on run 4 using electrical retrofit strategies, as it contributed to at least twice the savings of strategies of building envelope. The efficient air conditioning system was used for the final run. As seen in the figure, the net zero energy goal was barely achieved. A cumulative savings of 338,000 kilowatt per hour was met, as compared to the 333,000 energy reduction required. It has been proven that it is technically feasible to achieve the net zero energy goal using building energy simulation. This process was repeated for the other retrofit scenarios aforementioned. In this figure, it illustrates the multifarious performance of retrofit scenarios. Beneficial criteria are those with higher values are desired. Alternatively, lower values are preferred for non-beneficial criteria. Choosing between several alternatives based on multi-attributes, especially when the data regarding the alternatives are uncertain, imprecise, and subjective is difficult. Thus, a structured technique is necessary to aid stakeholders to make the best decision in accordance with preference. 12 stakeholders were identified to be decision makers in this study. However, due to unforeseen matters and constraints, only 9 responded to the survey. Of the 9, 7 responses were considered valid using consistency indices and random indices, while 2 were disregarded since it exceeded the allowable 10% consistency ratio. A questionnaire was prepared for each stakeholder to calculate the waste coefficients of the importance of each factor. 3 groups of criteria were set to assess ERS from environmental, economic, and technical perspectives. In Table 6, It shows the criteria weights of the 6 sub-criteria considered in the study. To illustrate the proposed model, the distance to target method (VICOR) was employed in the study. This method determined a compromise solution based on the obtained weights from the stakeholders' preference and the performance metrics of environmental, economic, and technical. As previously mentioned, 6 possible retrofit scenarios with multifarious efficiency was established to test the proposed MCDA framework. The on-site generation scenario was determined to be the best retrofit scenario as a result of significant energy potential and optimal investment cost. Furthermore, the environmental damages of this scenario are adequate when compared to other retrofit scenarios. On the other hand, the net zero energy scenario was the ideal scenario in terms of energy potential. However, it ranked last due to the immense environmental impact, and its economic feasibility is quite questionable. To sum up, 3 retrofit scenarios comprises the compromise group: the on-site generation scenario, the mechanical electrical scenario, and the building envelope scenario, ranking first, second, and third respectively. A sensitivity analysis was performed to test the robustness of the results of the AHP Vicor model developed in the study. This was done to analyze the impact of modifying an input on the results. A sensitivity analysis was first done on the ranking of energy retrofit strategies. It can be clearly observed that each weighting method resulted to a different compromise group. Similarly, the same method was performed to retrofit scenarios as seen in Table 8. All but 2 resulted to contrasting results. The on-site generation scenario, the mechanical electrical scenario, and the building envelope scenario unanimously constitutes the compromise solution, regardless of the weighting and ranking method used. To sum up, sensitivity analysis showed robust results. It can be concluded that adapting various MCDA techniques might result to a difference in rankings. However, the AHP Vicor model developed in the study showed compelling results. To sum up the study, a proposed MCDA model using AHP and Vicor with environmental, economic, and technical performance criteria of ERS in buildings was developed. It was found out that a compromise alternative may differ according to the responses of stakeholders, performance criteria considered, and the number of alternatives examined. Also, weighting and ranking methods used. While the net zero energy scenario proved feasible, this scenario was not generated as a compromise alternative. Over the course of this work, the objectives of the study were clearly met. However, future works similar to the study may, first, explore different types of building with various occupancy and construction with social aspects of energy retrofitting to provide a holistic sustainability assessment. Next, for the whole life cycle of the building, additional parameters such as maintenance and operations and the life cycle cost is recommended. Lastly, laboratory and actual validations are suggested to further strengthen the information regarding energy retrofit strategies. This now concludes my presentation. I'm now open to your questions. Thank you for listening.